Okay. So, hello, good morning, and I'm really happy to be giving these lectures. I'm a high energy theorist, which means the language is a little bit different from nuclear physics. And I understand most of you are nuclear experimentalists and theorists. I hope to go very, very slowly today. So my goal is not to show all these slides, but to have you ask lots of questions and interrupt me and get some discussion going. So please, please ask questions all the time. There's no stupid question. There's no question that's disruptive. It really improves the flow if there's a back and forth of questions, because otherwise, I can flip through all the slides and, so what? So I'm going to talk about an introduction to SMEF. Now, what is SMEF? It's the standard model effective field theory. And when high energy physicists say standard model, what we mean is the standard model of particle physics, SU3 cross SU2 cross U1. So today I'm going to give you an introduction to what this theory is, and hopefully by the end of my lectures tomorrow, you will see why it is actually relevant for the EIC and why Fred scheduled my talk. But today it's mostly standard model. And yes, here is my email. Feel free to send questions, complaints, suggestions to my email. And in fact, some of these slides, the standard model slides, I've shown many, many times. And when I was going through them yesterday, I said, oh, there's a mistake and nobody noticed it. So, I hope the slides are perfect. I want them to be perfect. But if you think something isn't perfect, you should tell me. I have a very thick skin. Okay. Yes. You guys, I hate to say it, but I'm pressing the forward button. Yes, this one. Yeah, and it's going to work.
You click back on the slide.
Sometimes you gotta click on the slide first.
I got it. That's just, okay, I'll keep going. I can control it from over there. Okay. Let me try that.
There we go.
All right. So from a particle physics point of view, everything in our world changed when we found the Higgs boson. It didn't change because we knew the Higgs boson weighed 125 GeV. It changed because we knew this particle existed. The very existence of the Higgs boson changed our whole view and our whole understanding of particle physics. And that's what I'm going to talk about today. And all of this comes in the context of physicists being very self-critical and always thinking about the next step, because of course the next step takes a very, very long time to get there. So in the last few years, we've seen the European Strategy Study and the SNOMAS study, both of which are our communities coming together to try to figure out not only what machines can we build next, but really what we want to learn from these new machines. How do we think about the future? So as I talk today about the Higgs boson, you'll see that it really looks like we know everything about it, but yet we don't really know everything about it. So I'm going to explain how our knowledge at this point in time on the Higgs motivates us to study for the future. And then this gives questions that, for example, the EIC will be able to answer. So what happened in the last 11 years? 2012, we found the Higgs boson. We know its mass. I just told you I don't care what the mass is. We know it exists. But the really important thing about it is that it appears to be exactly as predicted, that nothing that we've measured suggests that there's anything else going on other than our standard model of particle physics. And as a particle physicist, I find this really weird. And our community finds this really weird because we start going down all the questions in the world that we don't understand. This model that we think is so beautiful doesn't understand dark matter. And in fact, it has nothing to say about dark matter. It doesn't tell me why the top quark is heavy and why the electron is so light. It doesn't tell me why the strong coupling constant is so much bigger than electromagnetic. And I could go on and on and on with this list of things we don't know. So the fact that everything we measure looks exactly like our model is really weird. And in fact, from a particle physics standpoint, this was really unexpected. We had all sorts of working groups and studies before the LHC turned on and said, well, we're going to have so much new stuff. How do we figure out what's going on? And so then when we didn't find this new stuff, it was really disappointing. And that's what led us to this idea of effective field theories, which is what I'm going to concentrate on. Okay, so the standard model, how many of you are high energy physicists? Any of you? Oh, so it looks like about half. Okay, so the standard model is a gauge theory, and it's an SU3 cross SU2 cross U1 gauge theory. So the SU3 sector, the strong sector, you've heard a lot about last week, and this is defined by the strong coupling constant. The SU2 cross U1 we call the electroweak sector, and in the electroweak sector, it's described by only 3 parameters plus the masses of the particles. And you can pick these 3 parameters as you like. You can trade them back and forth, take what you want. But typically, we describe this theory in terms of G Fermi, which is the muon decay constant, alpha electromagnetic, and the measured value of the Z boson mass. So the electroweak sector has got the masses and it's got 3 parameters. So all of the particle couplings are fixed in terms of these 3 parameters. And this is actually a very deep statement, because what this says is that every interaction is fixed. There are no fudge parameters other than the Higgs mass in this theory. I can predict absolutely everything. So a theory where you can predict everything is a theory where you can test things. So this is why once we discovered the Higgs, it changed everything. Because now we had every single ingredient, we know every single coupling, so we can test things, and we can test things very, very precisely. So over the last decade or so, the LHC has tested the standard model in many, many, many different places. So this is an atlas plot showing production of the standard model particles. So there's W production, Z production, TT bar production down here, pair production of 2 gauge bosons, down here, the production of top quarks with gauge bosons. And here are the cross sections coming across here. And you see that the cross sections span many, many orders of magnitude. And here you see the theory are these gray boxes, and then the circles are the measurements at the different energies. And what you should learn from this is that the theory really predicts everything that we have measured very, very precisely. And here's the same graph from let's see, that was Atlas. This one is CMS, showing all of these production processes and normalized to theory. So the orange bands here are the uncertainties, the theoretical uncertainties. And note that most of these processes have been calculated to next to leading order in the QCD coupling. So as far as we know, everything agrees, not just, sort of, but very, very precisely. Okay. So we know that the standard model of particle physics, it works. And it works very, very well. So what do the experimentalists do? They go out and they look for new stuff, and they've looked for stuff that you can't even imagine. So over here is CMS. They're looking for things like excited fermions, or maybe there's some new heavy gauge bosons, or maybe they're leptoquarks. This is something that the EIC is going to look for. Maybe there's some strong multi-jet resonance where you have glue goes to something heavy and you make a resonance. Maybe there's some large extra dimensions. Maybe there's some compositeness. So they look for all this stuff on a case-by-case basis. And you notice these are the limits here. They don't see any of this stuff. Similarly, over here, Atlas looks for stuff. And the Atlas plot is kind of amusing because you can't actually read any of these things. You have to really stare at this. But what you see here is that here's the TeV scale. And all of this stuff is heavier than the TeV. So what do we know? We know that the standard model works. It predicts all these cross sections. They agree at the percent level. We go out and we look for new stuff, and we don't see any of it. Okay, so let's get back to what we know about the standard. So the standard model, I told you that the electroweak theory was predicted or could be described in terms of just 3 parameters, which I said we're going to take them to be alpha electroweak, the Fermi constant, and the Z mass. So what that means is that in this theory, I can predict the W boson mass. So the W boson mass isn't just something you measure, but it's something that you can predict. It's a prediction of the theory. So at the quantum level, you get contributions from both the top quark and the Higgs boson. So the W mass at lowest order in the standard model theory is predicted to be 80.94 GeV. And this is just a simple tree level calculation. So then I start calculating higher orders. And by now people have calculated many higher orders than this. I think 3 loops is the status. So they're top quark loops, they're Higgs loops. The top quark loops are interesting because they grow with MT squared. So, and why did I normalize that to 246? It doesn't matter what I normalize it to, but it grows with MT squared. So you get a rather large contribution from the top quark mass. You get a contribution from the Higgs boson, which grows logarithmic. So you have these 2 dominant contributions to what the W mass is predicted to be. And so then you can test the theory at the quantum level. So let's stare at this plot for a little bit. So this is a plot from which you're supposed to get that not only does the standard model of particle physics work at the tree level, but it also works at the quantum level. So what does this show? This has the W mass on the x-axis and the top quark mass on the y-axis. So these bands here are the measured values in the experiments. So here's the measured value of the W mass, and here is the measured value of the top quark mass. And for those of you who follow this thing, you know that the W mass, there was a measurement from CDF which disagreed a lot with the previous measurements. So these people just averaged the new measurements with the old measurements, which doesn't actually change your conclusions too much. Okay, so then you can take your predictions for everything except the W mass and the top quark mass, and then see how they agree with the explicitly measured values. I think I'll use. Okay, so if you do a fit to everything you know in the world, except for the W mass and the top quark mass, you get this orange curve if you leave out the Higgs, and you get this blue curve if you include the Higgs. So what does this say? This says that at the quantum level, the inferred values of the W mass and the top quark mass, this blue thing, agree pretty well with the experimental values. And you can see there's a little bit of tension here with the W mass. It's a little bit low, the inferred values, but pretty much everything that we can predict agrees. So are there questions at this point? Anybody? Yeah.
I don't really understand when they average the 2 values. What do they do with the uncertainties?
Well, this is a bunch of theorists, very smart theorists, but it's a bunch of theorists. So they just take the uncertainties that are given by the experimental collaborations and they just do quadratic averaging.
Is that okay?
No.
Okay.
No, it's not. And in fact, the particle that, I mean, that's really the question is how do you deal with the correlations between measurements and the uncertainties and so forth. So how many of you know about the particle data group? Most of you? Yes. So the particle data group is the group. So they are working on figuring out the best way to average these uncertainties because there are various points of view as to how you would do this. But from my point of view, the thing to learn about this is it works pretty well, but not perfect. So there were, you're one.
Okay. Just gonna switch the camera.
Oh. Thanks, Fred.
No.
Okay. So there were a lot of theory papers which tried to fit this new CDF measurement, throwing out all the other stuff. And you can do it if you play around with new stuff. Okay, but okay. So the bottom line here is that everything we know at this point is that the standard model of particle physics is an absolutely perfect, gorgeous, wonderful model. So how are we going to learn anything new? We don't have an accelerator that's going to go to higher energy than the LHC for, centuries. So we have to see what we can do with our data. So is there more? So how can we figure out if the standard model with the Higgs is just the low energy theory from some higher theory, which is at, I don't know, 100 TeV, anywhere much higher scale, or are we just stuck? Okay, so to go further, we have to talk about decoupling. And what is decoupling? Decoupling is the idea that if there's something very, very heavy the stuff we measure at low energy doesn't depend on this really heavy stuff. And you can see that our theories wouldn't make any sense if we didn't have some concept of decoupling. Because what if we had supersymmetry at 100 TeV, say, but it affected our low energy measurements? So this would be inconsistent. So we have this concept of decoupling, which is actually pretty simple to understand. So suppose you got some new particle X. Pick your favorite particle X, and it's got some mass m sub x, very, very heavy particle. Okay, too heavy for us to actually produce. So in the standard model scattering, this is maybe call it Drell-Yan. So as QQ bar goes to Z, goes Z plus E minus. So this interaction goes like the coupling constant here. So there's two coupling constants, G squared, and then there's the 1 over the mass of the Z squared. So now I've got my new particle that's going to contribute X. So this contribution goes like whatever the coupling is here, gx squared over m sub x squared. So then when I calculate my cross section, I'm going to get the standard model rate, and I'm going to get the interference of these two guys. So I'm going to have the standard model coupling, my new coupling, divided by the mass of my heavy guy. So as this guy goes very heavy, this goes to the standard model. So this is decoupling. Okay, anybody want to tell me where this argument fails? It seems real simple, right? Okay,
It's large.
what's that?
When GX is very large.
Exactly. So this argument assumes that these guys are small. But if you have a particle whose couplings are proportional to mass, the argument is fallacious. And we have a particle whose couplings are proportional to mass. In particular, we have the Higgs boson. So the Higgs boson couples to fermions, say electrons, top, whatever, proportional to their mass. So this coupling is the mass of the fermion divided by V, which is related to G Fermi, which is 246 GeV. Similarly, the couplings of the Higgs to the W and Z gauge bosons are proportional to their mass squared. So if I go back, if I start putting in mass factors at these vertices, this thing does not decouple as the mass in the denominator gets very heavy. So the Higgs is our first example of a particle that does not decouple. And this is kind of cool. So we've seen a particle, the Higgs, its couplings are proportional to mass, and it does not decouple. So if the Higgs mass had been very, very heavy, it's still seeing the effects of the Higgs boson. And I'll have an example of that later. So why does the Higgs coupling to W's go like the mass of the W squared? Because you know couplings to say the photon don't have any mass. It's once you break the symmetry and give the gauge bosons masses, they have a longitudinal polarization. So the photon only has transverse polarizations, but gauge bosons have longitudinal polarizations, and longitudinal polarizations are exactly what give you factors of mass in the couplings. So this idea that there's something going on with the Higgs and non-decoupling suggests that looking at Higgs physics is a good place to look for new physics. Okay, so let me review the Higgs couplings here before I go on to new physics. So the Higgs is particularly interesting because, as I said, all of his couplings, every single one, they're all predicted. There are no free parameters in this theory. So if you only remember one thing from my lectures, it's no decoupling and everything's fixed. So the couplings to fermions are proportional to mass, the mass of the fermion over this scale V. So that tells me that the most interesting couplings are the couplings to the top quark, because the top quark is the heaviest fermion. And the least interesting couplings are, say, the couplings to the electron, because they're so small, we have no way to think that we can ever measure them in the future. The couplings to the gauge bosons are proportional to their mass. So here's the coupling of the Higgs to the W gauge boson, MW squared, the couplings to the Z's, MZ squared. But now you say, so the Higgs can't, question? No, okay. Any questions? Okay, so now you say, how does the Higgs couple to gluons or to photons since it couples to mass? And the answer is it couples through loops. So it couples at one loop to gluons. So here's the Higgs to two gluons, and it's one loop, so it's got an alpha S, and there's some function there. Then it couples to photons at one loop, proportional to the electromagnetic coupling, and then it couples to the Z and the photon through a mixed coupling here. And in fact, this coupling has just been observed at the LHC a few months ago, the coupling of the Higgs to the photon plus the Z. So these things all happen at one loop, and they all depend on the mass of the particles in the loop. In particular, the mass of the top quark is the most interesting thing. And the Higgs self-couplings, we also know. So the Higgs couples to itself, and these couplings are also proportional to mass. So the potential of the standard model, there's a mass term for the Higgs. There's a trilinear coupling of the Higgs, and I forgot to make that a capital. And then there's a quartic coupling of the Higgs. So the trilinear coupling is proportional to the mass squared of the Higgs, and the quartic coupling of the Higgs is also proportional to the mass squared. So again, the only unpredicted parameter here is the mass of the Higgs. So let's go test this theory some more. So how do we make the Higgs at a hadron collider? Well, here's the coupling to gluons that I'm going to have a lot to say about in the context of effective field theories in a bit. So the Higgs couples to the top quark, and then there's a loop that goes around, and it's mostly the top quark because, as I said, that's the largest coupling. So this kind of interaction depends on new physics in the loop. So if you had some, say, supersymmetric model where you had some charged 2/3 scalar or something, it would contribute to this, and it would change the measured rate, which I'm not going to show you the rates, but they come out to be exactly the standard model, by the way. So you can make two gluons, can make two top quarks and a Higgs. So this would measure this top TT bar H Yukawa coupling, which is MT over V in the standard model. And then you can have things like this where the Higgs spits off a W or a Z, which is exchanged between two quarks. So all of these rates have been observed at the LHC, and they've all been observed with exactly what we expect. Yeah.
Maybe potentially explain the lower left one. That's not the Higgs coming off at a different Reggie pole, right?
It's the Higgs.
So
This is, you guys know Weisacker-Williams, right? Yeah, this is exactly the Weisacker-Williams. So the quark here spits off a W, and this quark spits off, say, a W, and it's enhanced in the forward direction by a logarithm. And then these two W's, this is a standard model vertex, two W's make a Higgs, and then this Higgs decays to tau's, B's, W's. I just didn't draw the decay. So it's the physical particle. And in fact, it's kind of interesting because the rate for this is very specific in kinematic space. Because it's essentially Weisacker-Williams, this guy and this guy are in the forward direction. So you tag these forward jets, and this Higgs is very, very central. And there's almost no jet activity in the central region near the Higgs. So it turns out the background is really small for this. Yeah.
what is V?
Yes. V is G Fermi over the square root of 2 is related to 1 over V squared. So V is the vacuum expectation value of the Higgs boson. So when the electroweak symmetry is broken, the Higgs boson gets a vacuum expectation value, which is V. And V is measured by mu on decay.
But if this V is very large for like a new particle, wouldn't this argument of mass being
V is fixed.
okay?
It's fixed. And I'll show you a few slides down, and you can ask my question again, your question again, but it's fixed by mu on decay. So we know exactly what it is, and we know that it's 246 GeV.
Yeah, but that's for the Higgs, right? I mean, because you're talking about new physics and a new in like the Higgs, and maybe V is towards in.
I could have a model where I had two Higgs bosons, and then V would be different.
Mm-hmm.
It would still be constrained not to be too big.
Okay.
But so then the sum of my V's would be 246 GeV essentially.
Okay.
So it can never be big.
Okay. Thank you.
But that's a good question. I should have gone through this. Okay, so now let's see how we test this. Since I told you that everything, works perfectly, it's so boring. It's just works perfectly. So how do we test this theory? How do we go beyond our standard model without actually having any new physics? Because if we have, like I said, a 2 Higgs doublet model, we'd look for these new Higgs bosons, and that would be way more interesting than what I'm going to talk about. We'd see something new. or if we had some new resonance somewhere, we'd see this new resonance. And again, that would be way more interesting than this. What I'm talking about is this really sad scenario where we don't see anything. How do we pull out the absolute last little bit of physics, or lots of physics, if you like? How do we pull out more physics from these measurements? So the first approach, people said, well, let's assume there are no new resonance, nada. No, we won't have any of those. No Higgs is nothing. Let's assume that the Higgs is very, very narrow. And in fact, it's 4 MeV in the standard model, and it's actually sort of been measured now. So we kind of know that the Higgs is very narrow. And furthermore, this is a big assumption. We'll assume that the interactions we have don't have any new tensor structures. So we just have the standard model. We'll play around a little bit with the factors. So we're measuring some Higgs process, sigma times branching ratio. So we'll have, say, glue goes to Higgs, goes to BB bar, all the things we measure. So we're assuming that it's a Higgs resonance. So we're using the narrow width approximation. We make a Higgs and we multiply by the branching ratio to the final state. So we've got the cross section for making this guy, and then we've got the branching ratio for the final state. So what the experimentals and theorists did in 2012 and have only now stopped doing is said, well, we've got these vertices. So the couplings of fermions are the mass of the fermions divided by this V, which is fixed to 246 GeV, and we'll just put in a fudge factor, and we'll call this fudge factor kappa. Similarly, for the gauge boson interactions, we know the interactions in the standard model, and we'll put in a fudge factor. We'll call this thing kappa. So you've probably seen tables where they've shown you limits on the kappas. They're all close to 1. So these are fudge factors for the Higgs coupling. The thing is, this is a very bad, no good, terrible, stupid, terrible thing to do. And why is it a really stupid, no good, terrible thing to do? It's because the standard model, everything is fixed. There are no free parameters. The gauge invariance of this beautiful theory we've constructed requires that these guys are 1. So when you start putting in these fudge factors, you spoil gauge invariance, among other things. So it's the first approach to trying to tease out new physics, but it's a terrible thing to do because it violates gauge invariance, it violates all sorts of stuff. If you know about unitarity, it spoils unitarity cancellations, which I'll tell you about later. Okay, so how does this work? This is the kappa framework. So here's an example of glue goes to Higgs, goes to 2 photons. So you got 2 gluons, they're making a Higgs. You got your fudge factor, which we'll call kappa G. You got your Higgs decaying to whatever, the photons here. You got your fudge factor for the Higgs coupling to 2 photons and your fudge factor for the total width, but you're calculating branching ratio. So all that happens is that all your rates are rescaled by products of these kappas, these fudge factors. And notice that since you're assuming the narrow width approximation, you're making a Higgs and the branching ratio Higgs goes to whatever, you've got the total width in the denominator because it's a branching ratio. So people do these fits assuming that the total width is just the sum of the decay of the Higgs to all the standard particles. So you take the Higgs decay to B's, to taus, to whatever, you just add them all up. But you could say, well, maybe there's some light stuff that I missed and we'll put that in. So you get slightly different fits. And so when you look at these fits, you got to read the fine print because they put different things in. Questions? Okay, so the problem with this is, as I said, the gauge invariance requires that the Higgs couplings be exactly as in the standard model. They're not free parameters. And furthermore, since it's not a consistent field theory, that means I can't calculate loop corrections, radiative corrections, because I've just got fudge factors. So I can't start calculating corrections to this approximation. The electroweak corrections in particular do not factorize into an initial state times a branching ratio to a final state. They're diagrams where the gauge bosons go from initial state to final state, so they don't factorize this way. Furthermore, if I haven't convinced you yet that this is not the way to go, there's no kinematic information whatsoever in this kind of approach. So you measure Higgs decays to whatever, and we're just rescaling the total rate. But of course, you're missing a lot of stuff if you don't look at the kinematics of a scattering process. If you just multiply it by a fudge factor, You're missing, is it the same at small angle? Is it the same at high PT? So you're missing a lot. And lastly, when you do it like this, you just have these fudge factors and you don't learn anything from all the other physics we have in the world. You don't learn anything from, say, the W mass or from measuring TT bar production or anything. It's just fudge factors in this one little world here. So obviously I have a better way to go. So what you want to do and what connects everything and why I'm talking to nuclear physicists, EIC physicists, is because there's a better theoretical way to go at looking for new physics. And this better theoretical way connects physics at the EIC with physics from Drell-Yan, with physics from the top quark. So while I'm talking about the Higgs here, this framework of effective field theory that I'm going to describe for you really connects things in different areas. So it's very, very powerful. So what do we assume when we're doing the effective field theory, in particular an effective field theory for standard model like physics? So first of all, we assume there are no new particles at current energies. And this is a really good assumption since we haven't seen any. So we'll assume if there's some new particles in the world, they're way, way up, way at high energies where I can't see them. Okay, so what you want to do is look at these very precise measurements of standard model predictions and see if we can tease out what this new high scale physics might do. And this framework lets me connect data from different sectors, from Higgs, top, the electroweak data from left, everything. It's all in the same framework. So a measurement of the, like I said, the W mass might connect with the measurement in the Higgs sector. So then I can potentially learn a lot more. And these are consistent theories where you can calculate corrections to your expansion. So you've got a consistent gauge invariant expansion. So then I can start systematically improving my predictions. And this is what a lot of people are doing right now. So let me start, and this is the answer to the question about V, with the simplest example of an effective field theory. And you all know and love this one. This is muon decay. So here's the muon decaying to an electron and two neutrinos. Muon decay was measured, before you guys were born. So what do? Is they measure the energy and angular distribution of this electron relevant to the initial state muon. And by these measurements, they know that it's a left-handed current. So these sizers say the muon and its neutrino, the electron and its neutrino, and the rate of the scattering is just parameterized by G Fermi. So this is just a factor that's put in here. So when you calculate the cross section for muon decay, it grows with energy. So it goes like G Fermi squared times the energy squared. So the theory only makes sense for some energy. At a certain energy, G Fermi squared, energy squared is too big, bigger than one, say. And it turns out this energy is about 600 GeV. But that's okay. We have the standard model. The standard model comes in and saves the day because we know that at the energy scale of the Z and the W, say 100 GeV, we've got the gauge boson. So the process isn't really muon decaying to electron two neutrinos. It's a muon decaying to a neutrino spitting out a W, and the W is making an electron and a neutrino. So in the standard model, what you have is that the interaction is, again, the left-handed currents between the electron and the neutrino and the muon and the neutrino. But here we've got the coupling here of the W to the muon, which is fixed in the standard model. It's G over square root of 2 at both vertices, G squared over 2. And here's the propagator, Q squared minus MW squared. And now you have your effective field theory. You know that for muon decay, the effective energy, Q squared, is much, much less than MW squared. We're talking about a muon decay. So we can match the effective field theory, which is the four fermion interaction, with our standard model interaction. And we know that G Fermi is just given by G squared over 8MW squared. So if you go through the standard model interactions, what this says, G Fermi of the square root of 2 is actually 1 over 2V squared. So this is what fixes V, is the correspondence between muon decay in the four fermion interaction and muon decay in the standard model. So this is a very simple example of an effective field theory. So at energies much below the true theory, I can approximate it by this four fermion interaction. And that's exactly what we're going to try to do in the standard model. We're going to say, we've got something way above here, and then we'll approximate this theory from the high energy by our theory at the standard model. Questions? Okay. So here's the framework for this effective field theory framework. We'll assume SU3, SU2, U1 gauge theory. So exactly like in the standard model. So we won't mess with the gauge theory. And we'll assume that the Higgs boson is part of an SU2 doublet. So because all the measurements that we make suggest that the Higgs really is in an SU2 doublet. So when we make this assumption, this is what defines what's called the standard model effective field theory, the assumption that the Higgs is in an SU2 doublet. So then the standard model, our theory that we're measuring so well at the LHC, it's just the low energy limit of some effective field theory at higher energies. So my Lagrangian is my standard model Lagrangian. Then I just make an expansion in towers of higher and higher dimension operators. So we start with dimension 6 operators, which then are scaled by a factor of 1 over some energy scale, 1 over lambda squared, and then dimension 8 operators, which are scaled 1 over lambda to the 4th, and so forth and so on. There are many, many operators. So all of these operators are made up of standard model particles by assumption, and then all the new physics results in these coefficient functions here. So there are many, many operators that I can write down. At dimension 6, there are 2,499. So you can see that one is going to have to make some assumptions because 2,499, it was a great triumph of particle physicists to count them. Yes.
Odd dimensions.
Yes, yes. I was hoping somebody would ask me that question. What about odd dimensions? Well, at dimension 5, there's only one operator I can write, and that's connecting the lepton doublet, which is the electron and the neutrino, with the Higgs, because I've assumed this gauge invariant. So this one operator that I can write at dimension 5 violates lepton number. So if I assume that lepton number is conserved, which seems like an okay assumption, but if I assume lepton number is conserved, I don't have any of the odd ones. So people who do neutrino physics and who try to understand, say, the neutrino masses and so forth, they tend to like to put in the odd numbers using this lepton number violation to get a theory to get neutrino masses. That's more questions? Yeah.
Did you say how many fields? 2 fermions, 1 Higgs, 2 Higgs?
For the dimension 5, let's see if I wrote that one down because it's in it. I didn't write it down, and there's no blackboard. There's 2 leptons and there's 1 Higgs in those. Let's see.
Dimension 4, or am I counting wrong?
3, 4. No, it must have 2 Higgses.
Okay.
2 Higgses because it's dimension 5. Yes. So it's lepton doublet, Higgs doublet, lepton doublet, Higgs doublet. Yeah. Yeah, I should have written it down because it's kind of interesting. Yeah. But they all the odd ones violate lepton number. Okay, so you got to make some assumptions here. You can't use all these operators, and that's where all the sausage making comes in here and all the queasiness of people using this. It's the fact that we don't actually know how to do this in a perfect way. So typically when people start fitting to data, they'll pick sort of 20 to 30 operators, and they'll have a lot of reasons, some of which I'll give you, for picking the specific 20 and 30 operators they use. But the real power is that you can connect, as I said, the different sectors. Okay, so here's counting dimensions to go with your question. So if you count dimension, a fermion has mass dimension 3/2. A scalar is mass dimension 1. Oh, I did write it down. Oh, good. Here we go. And the gauge boson has mass dimension 1, and a derivative has mass dimension 1. So for example, in the standard model, here's the kinetic energy, psi bar d mu psi, 3/2 1, 3/2 has got dimension 4. So here's the dimension 5 one. So it's a lepton doublet. This is neutrino electron and so forth and so on. So it's phi twiddle dagger T, and this is charge conjugation. So it's actually a little bit convoluted to write it with all the indices, but again, there you go. So we start at dimension 6. Okay, so let's see how we do this. Let's start constructing some of these operators and see what they do. So let's start with the top quark interaction with gluons. So here's two top quarks, here's a gluon, and here's a strong coupling constant. So this is a standard model interaction. So this is dimension 4, 3 halves, 1. So the easiest way to start constructing my dimension 6 Lagrangian is just add on a phi dagger phi, 2 Higgs fields, because this will be 1 + 1 is 2. So the first thing I'll do is I'll take my standard model Lagrangian and add phi dagger phi to everything. So here we go. And I'll just put some arbitrary coefficient here. And since this operator has dimension 6, I have to divide by a scale, which typically we call lambda. So when the Higgs field gets its vacuum expectation value, when the symmetry is broken, this phi dagger phi goes to h + v squared over 2. So not only do I generate terms with the Higgs, but I also generate terms which are just rescalings of things with v squared. So now what happens is that my top quark interactions, TT bar G, get a contribution from my new standard model effective field theory term, which has a piece v squared, vh, and h squared. So the v squared piece, this is just a constant piece. So what this tells me is that what I thought was alpha s before, this gs squared, really has a piece that comes from this new physics interaction too. And this is general in this effective field theory, is that I rearrange the interactions or the relationships of the Lagrangian couplings with the physical stuff. So the coupling of the top to the gluon isn't alpha s, but it's alpha s with a piece from my new physics. But I can do this consistently. You can also see that in this kind of picture, I've got TTGH. So this is an interaction not proportional in the standard model. I've generated new vertices, but the relationship between making a Higgs coupling to 2 tops and a gluon and 2 Higgses coupling to 2 tops and a gluon, they're related. There's just this factor between them of 2V. So this happens pretty much with everything in the standard model effective field theory. I make new Higgses. I have operators that are related to each other. I redefine my coefficients. So it gets complicated, but on the other hand, it's very, very straightforward. It's a formula for doing this. I write down all these gauge invariant operators and I just keep going. Okay, so for example, here we go. We've got the gluon kinetic energy term, G mu nu, G mu nu. I'll just add a phi dagger phi. We've got the electroweak, SU2 and U1 kinetic energies. I'll just add phi dagger phi. So this is formulaic, but some interesting things happen because if I add terms like this to my gauge interactions, when I take both of these phi's to be V, then my gauge kinetic energy is no longer canonically normalized because I've got a contribution here, which is V squared times what I thought was my kinetic energy. So I've got to redefine all my fields to get all my gauge fields canonically normalized. And then you've got mixed contributions between the gauge fields that you didn't have before. And it probably won't surprise anybody to know that since this is formulaic, there are computer codes where you can just turn the crank and get these interactions. Questions?
What is S parameter?
What?
S parameter.
Oh, okay. So in particle physics, we want to look for new physics in the simplest possible ways. And so probably most of you know about the rho parameter, which violates isospin. So you can do fits to what are called the oblique parameters, assuming all the new physics comes from the W and Z propagators, which in some models is a pretty good approximation. So the T parameter is just the rho parameter, and the S parameter essentially measures the running of the W 2-point function from the W mass to 0. So for Q squared of the W mass to Q squared of 0. So this is something that's very well measured. So it's just new language. We had this language where we look for these modifications of the propagators in terms of these oblique parameters. And now we're going to call it HWB in the effective field theory language. But Michael Peskin invented this, I don't know, 30 years ago, whenever. He called it the S parameter. So some of what I'm telling you is new language for old physics. So this particular piece is old physics. It's the mixing of the SU2 and U1 gauge boson. Did that answer your question? Yeah.
Since you said we're adding like factors of phi dagger phi
Mhm.
and then keep going, I was concerned about if this all converges, like we are like adding stuff to our already known constants and we have to redefine them. Do we know that?
That is a really deep and profound question. Yes, there's a lot of angst in the particle physics world over that. Because I've added the dimension 6 terms. So these dimension 6 terms go like v squared over lambda squared. So if, for example, the new physics was strongly interacting and this coefficient for some reason were big, this could be a number of order 1. So how do I know that we don't need the next term, the dimension 8 terms or the dimension 10 terms? So this is where this stuff, which we have said is model independent, beautiful, some of the queasiness creeps in, right? Because you're exactly assuming this. You're assuming that these are small corrections. And in fact, tomorrow I will show you a plot where I calculate negative cross sections, which you all know negative cross sections. Give me a hint. They're wrong. If I calculate a negative cross section, they're wrong. And the negative cross sections come about exactly when this expansion is no good. Yes. So this is something that's very important actually to think about in these things. And people stand on their head to try to make sure they're in this region of validity. Oops, sorry, wrong way. But the reason we stand on our head and go to so much trouble to do this is we don't actually have any better way to look for new physics in the absence of seeing new particles and new resonances. If we don't see anything new, and I'll be the happiest person in the universe if we saw a nice new resonance, this is the only way, consistent way we know to see if we can tease out information about the high scales, even though it's messy. So it's going to get messier. So I said there were 2,499 operators at dimension 6. I like that number, but there's not a unique basis for writing down all these operators because I can write down any operator, dimension 6, write down anything that's gauge invariant under SU3, SU2, U1, and then I can just use the equations of motion to generate a new operator. So for example, if I write down this operator, here's a nice operator. It's the derivative of the gluon kinetic term squared. So d nu g mu nu squared. Okay, I get the equations of motion, and using the equations of motion, I get that it's related to a 4 fermion operator. So it's G strong F bar T A F. So the equations of motion can be used to take operators which involve derivatives into operators which involve 4 fermions, and you can keep applying equations of motion to your operators, until you're bored. So you need to find an independent set of operators where the operators aren't related to each other by these equations of motion. And which basis you use yeah. Uh-huh. No, we include the new terms in my equations of motion. Yes. So you do it consistently. Yeah, right, because it would be wrong if you didn't. Yeah, yes. No. This is when you have your Lagrangian, you write your Lagrangian with, say, some new interaction. Then I write the equations of motion for my Lagrangian, and then it relates different types of interactions. So it's just a rewriting in a consistent way of which terms you have, which effective operators. And of course, the physics has to be independent, is the point. It actually took people almost 20 years to go from this step to this step to make sure that they'd actually had an independent set of operators where they couldn't transform from one to the other. So I wrote down a bunch of them here. I don't know if it's too interesting, but you can see there are a lot of new operators here. I didn't write them all, but I talked about operators where you just took the standard model and added phi dagger phi. But of course, there are a lot of other kinds of operators you can add. You can add operators. Let's go. Where's an interesting operator? Here we go. So here are 2 fermions, and here are 2 Higgs particles with a derivative. So the interesting kinds of operators are the ones where you put in derivatives. Because when you put in derivatives in your new interactions, what are you doing? You're changing the kinematic structure of the interactions. So this is something you might be able to measure, a change in the kinematic distributions due to the presence of this new physics. So let's see, what other kinds do we have? We've got operators with derivatives here. We have dipole top operators. These twiddles are CP violating. We have 4 fermion interactions. So there are a lot of possibilities here. But as I said, the interesting ones are the ones with derivatives, because these are the ones that are going to change the kinematic structures. Okay, so the power is this connection between, say, WW production, top production, say TTW production, Higgs production, TT bar. So it's the same operators that are contributing to these different processes. And eventually EIC will be a little blob over here constraining some of these operators. So all of this relies on this idea of scales and decoupling. So it relies on the idea that at some very high scale, usually the fits that people do take this high scale to be a TeV, because as you notice when I wrote down these effects, it was all 1 over lambda squared. So if you take lambda to be 2 TeV, things are 4 times smaller, right, than 1 TeV. So you very quickly get into the region where the effects are very, very small. So you can play this game 2 ways. You can assume you know what's going to happen somewhere, 10 TeV, 100 TeV, see what these coefficients of the model would be, pick your normalization group and scale them down to scales where we have data, and then try to fit these coefficients. Or you can say, I've got this whole mess of data. I'm going to go down here. I'm going to measure these coefficients. I'm going to get limits on these effective field theory coefficients. And then I'm going to take these limits and see what I can learn about the high scale model. And this is really what we're trying to do at the LHC, to do fits to all of our data from many, many different sectors, and say, well, maybe one of these things will turn out not to be 0. And then measuring this, I'll learn something about the high scale physics, because what happens is that if I have a model up here, I don't know, pick your favorite model, a 2 Higgs doublet model, a model with some rho resonance, some model. In the context of this very high scale model, I won't be able to make the new particles, but I'll be able to predict what the coefficients would be if that model were the way of the world. So in different models, I would have different patterns of these coefficients. So the whole hope and goal of this program is that we would measure a pattern of coefficients here. It would be something that would be non-zero. And then the smart theorists in the world, 20 years younger than probably you guys by the time they do this, would be able to say, aha, those coefficients correspond to such and such a model. So that's the hope. Okay, so the advantage of this kind of approach is it's a consistent quantum field theory. So I can calculate things and believe them. I can calculate them order by order in the scale parameter 1 over lambda. I can compute a cross section in this theory without knowing the high scale physics. It's systematically improvable. I can calculate loops, whatever, as long as I'm strong. And so at this level, it's pretty model independent. You calculate in terms of all these coefficients, and then you see what you can see and you interpret your measurements. So sounds good, but does it actually work? And what's hidden in there? What are the real assumptions that should make me uneasy? Okay. So let's start with another effective field theory. I showed you the effective field theory for muon decay. Let's get a little more complicated. Let's do the effective field theory for glue goes to Higgs. So as I said, the largest contribution is from the top. So this coupling here goes like the mass of the top. So this particular measurement, suppose I measured glue goes to Higgs, and I said, aha, for some reason I know it's from gluons, it still wouldn't tell me the TTH coupling, because in an effective field theory, I could have an effective GGH vertex, or maybe I would have some theory where there's a new quark in the loop. I can invent a theory where there's another charged 2/3 quark that would run in the loop here. So it doesn't really measure this because it's dependent on the loop. Okay. So we know that or I told you that the Higgs doesn't decouple because it contributes proportional to mass. And here's a perfect example. You just go calculate this cross section, not too hard. There's two gluons coupling to the tops. So it's alpha S squared because it's a cross section. The Higgs couples to the top like M top over V. So there's 1 over V squared from that coupling. You have to be on the mass shell, MH squared over S has to be 1 because it's a resonance here. And then there's some function here, which depends on the mass of the Higgs and the mass of the top that you can just calculate. But this function has the interesting feature that if I take the top quark mass to infinity, this function goes to a constant. So then this cross section goes to a constant independent of a mass. And so this particular process can be derived from my favorite effective Lagrangian. So if I had an effective Lagrangian where I shrunk this to a point, so I had phi dagger phi squared G mu nu squared, this effective Lagrangian gives me exactly the standard model rate in the limit that MT goes to infinity. So can anybody tell me why this logic tells me there isn't a standard model fourth generation? Okay, you guys can figure it out for your discussion section tonight. Because if you Fred knows the answer. So the stuff on this slide is enough for you to tell me why there's no fourth generation standard model life. Okay. So, okay. Let's see, where are we going? I'm going to show a couple more slides and I'll stop. So here's gluon fusion in the standard model effective field theory. So I've got my standard model Lagrangian. I've got my phi dagger phi added on to my two gluon fields like I love. And maybe I mess around with the top quark Yukawa. So this is a SMEF type operator that changes the top quark Yukawa. So here's the top quark Yukawa term, Q bar left, that's up, down, Higgs field top, and I added a phi dagger phi here. So this could in principle change the top quark Yukawa. But this particular example shows something that comes up every term when you do this effective field theory, because what this does is it changes the relationship between the top mass and the Yukawa. In the standard model, the Yukawa coupling is just the top mass. I showed you this, that CTEQ coupling is MT over V with a square root of 2 here. So here it is. But once I start adding these new terms, what happens is that this relationship has changed. And in particular, not only is the relationship between the mass and the Yukawa change, but the TTH coupling has changed. My arrow's in the wrong place. Okay, so instead of being MT over V, it's got this extra piece. So we have to systematically go through all of our interactions and make these changes once we start adding the new interactions. Okay, so gluon fusion, what does it measure? Well, I said it couldn't distinguish an effective GGH coupling from modifications to the top quark Yukawa. And in fact, what happens is now if I calculate gluon goes to Higgs, I get the standard model result. And here I've been lazy and I've just written the MT goes to infinity limit. And then I get contributions from these two new operators I added. And the important point to note here is you've got two operators contributing here. There's minus sign between them. So one measurement can't distinguish any of these coefficients. I need to make lots and lots of measurements in order to try to extract these coefficients. Okay, so I need to combine lots and lots of measurements. So it's a very complicated program. The other interesting thing and important thing to note about this is that when people are talking about these effective field theories, a standard question is, well, what scale does it probe? You like to ask, what scale does it probe? But here I can't answer that question. And the reason I can't answer that question is that everything is sensitive to some coefficient over lambda squared. So if I want to say what lambda I'm sensitive to, I have to make some assumption about the coefficient. And this is the question about the expansion, because if the coefficients are big, then I'm sensitive to a different lambda than if the coefficients are, say, 1, and I simply don't know. So when people do fits to these things, they'll do a fit and they'll tell you that the coefficient is less than, I don't know, 2.3 or whatever it is. What they really mean is that the coefficient at some scale lambda is less than that, because I always have to rescale by what I think the interactions are. So now you see the messiness is getting in here. Okay, I think I'll stop and take questions. It's 10 o'clock. Okay, but I'm finished for now. More questions, please? Questions?
We have time, so,
Right, I was supposed to stop at 10, right?
no, yeah, well,
Right,
we're,
because I can blather forever.
we're flexible. We're
You're
flexible.
flexible.
Schedule's very fluid, but.
Yeah,
go ahead
okay.
with Questions.
When you said we need to check to see why that slide tells us there's
Uh-huh.
no, did you say, so there's no, I just want to clarify that, no fourth generation of an SU2 weak doublet?
Yes, I can say, let's see, where was I? Yes, I can say absolutely, the day they made the first measurement of the Higgs cross section, that there's no fourth generation, which is just a copy of the standard model generations. Yep. Yeah,
And I just wanted to know, this kappa, the first idea,
Uh-huh.
is not as nearly as good as this one. I kind of like this kappa thing. Do people just assume that all of these major problems are going to be fixed at some high energy or?
no. People did the kappa approach in the beginning because it's very simple. You just fit the cross sections, you got your fudge factor, and you get a limit. And so for the first approximation, when we first turned on the LHC, we thought maybe these couplings would be off by a factor of 2, they'd be really dramatic. We said, oh, that's not so bad. We'll just see if they're about what we predicted. But now that we know they're pretty much what we predict to within 15% or so, now we have to do a theoretically consistent approach. So no, you can't fix the kappa approach. You can just say, well, it showed us that things are really pretty darn close to the standard model. Anybody? Yeah?
I guess in past talk I've heard on SMEP, there's some theory issues on like CP violating terms or like SMEP and non-perturbative effects. Like, what can you talk about those things?
Well, I can talk a lot about them. So I can talk forever. Let me find. Well, non-perturbative effects, the SMEF, I can't do because as soon as these coefficients here become big, it's not a perturbative expansion, right? So then the theory is no good. I can't do it. So that is an assumption that is baked into this kind of approach, that the theory is perturbative. So CP violation, no problem, no problem. Let's see, did I? Variant number violation, no problem, no problem. So this table includes a bunch of CP violating operators. I can write down all the CP violating operators. I can feed it into my CAN programs, which include these CP violating operators, and I can make my predictions. So there's no problem, as long as it's perturbative. Yeah. Yeah.
I'm wondering why you only include the term that you ate Fidegar 5? There must be some other way.
Oh, no, there are tons of other terms. Good. This is too small here. I started by putting in the phi dagger phi terms because they're easy, right? They're super easy. But if you look here, here's a term, say this is a doublet, a sigma mu nu, a singlet, a Higgs. So they're dipole-like terms. There are terms with derivatives. There's every single term that is gauge invariant.
Oh, okay.
So that's how you get to this huge number. Because there aren't that many terms which just set phi dagger phi to the standard model. Yeah. And in fact, like I said, the interesting ones are the ones with derivatives because they change kinematic distributions. And they're the ones that give me negative cross sections and tell me I'm all screwed up. Good. Yes.
I understand something wrong, but you said that the couplings to top quark are the most interesting is because of the mass of the top quark. Awesome. And can we repeat the same arguments as we have for muons in slide number 19 for taus, or taus are too heavy?
Oh, no, you can do it exactly for taus. Yeah. Let's see, what do I have?
19, I guess.
You said it was 19, huh?
Yeah, I guess. Yeah.
Yes, exactly. If I wanted to do it for taus, it would be exactly the same argument. But the reason people do it for muons is that muon decay is measured with a very, very small uncertainty. The error on tau decays is larger than for muon decays. But from a theory point of view, yes, you can just change these muons to taus. It's exactly the same. Yes.
if,
Oh, finish, yeah.
yeah, because you said also that the longitudinal polarization give us a coupling proportional to mass.
Mhm.
Doesn't mean that, for example, when we in the epic, we will observe the longitudinal polarization of our particles. Can we discover something?
Okay, I was not thinking EIC. I should have said the longitudinal polarization of the gauge bosons is proportional to mass. Because I know in epic, you're thinking of longitude,
Yeah.
yeah, differently. That's,
Thank you,
yes,
thank you.
sorry.
Thank you.
Yes,
No,
that
no,
was my sloppiness. Wait, questions in the back?
In slide number 17, you have talked about kappa rescaling.
This one is.
Is this the same parameter that we have encountered in ADS QCD? Kappa? Like,
No.
it says something.
This is really just fudge factors for Higgs couplings. This has no deeper meaning. I call it a fudge factor. It is really just taking my standard model Higgs couplings and putting an arbitrary factor there and seeing how big it could be. It's not connected to anything else.
Can we visualize it? What changes when we change kappa here?
What's that?
What change when we change the value of kappa?
Well, okay. Yes, absolutely. I did not do my standard model lecture here because I'm not talking forever. But in the standard model, the interactions say of the fermions, here's two fermions in the Higgs. It's fixed, absolutely fixed in terms of the mass of the fermion. There is absolutely no free parameter. So if I put a kappa here, I'm violating the SU2 cross U1 gauge invariance. So I can't do it. Well, it violates gauge invariance. And as you'll see, if I get around to it tomorrow, it also kills unitarity. So it's just not a consistent thing to do. Yeah. Anybody else? Yeah, back there. We had a question, then you.
I didn't really understand your question, like what is a fourth generation?
Oh, so in the standard model, all the fermions, the left-handed fermions are in doublets, right? There's a neutrino with the electron, there's the up quark with the down, left-handed down quark. So they're all in SU2 doublets. And there are 3 generations. There's 3 copies of the fermions, right? So what if I just copied it again a 4th time? So instead of up and down, top and bottom, what if I made T prime, B prime with exactly the same couplings as in the standard model?
Okay.
So I'm challenging you to tell me why I know instantly that that absolutely cannot be, period. Yeah.
Just fourth or any?
5th, 6th, 7th.
Okay.
It's
okay.
the statement is a copy. And that's an important statement. Yeah.
Just quarks, right? Just. quarks.
Well, the leptons don't really contribute to Higgs production. Well, before I get to your question, we know that if I add another set of quarks, I have to add the whole generation because of anomalies. So it wouldn't be consistent just to add quarks. So I can't do it, period. So if I just added the 4th generation of neutrinos, they could not be an exact copy. This is the important phrase here. I cannot take the standard model 3rd generation and copy the whole thing one more time.
That's 4 particles.
Up, down, electron, neutrino. Yes. Mhm.